now going to solve exponential and logarithmic equations. So two objectives in this section. First, we're going to focus on exponential equations. We're going to use some properties that make a lot of sense in the first problem. And the first problem is going to be if I have 4 to the 3x power equal to 64, and I want to solve for x. Now my exponent is, my unknown, is an exponent. And that's something I'm not used to. I'm used to linear equations. One variable, solve that, add this to both sides, subtract that from both sides, divide both sides by whatever, and solve the linear equation. We've solved quadratic equations by factoring and completing the square and the quadratic formula and graphing. But we've not solved for our unknown to be up high as an exponent. And it's kind of a challenging, well, it's not challenging, it's interesting, but it's not anything like what we've done so far. What we're going to do first is if there's any chance that I recognize, if my unknown is over here and I have this base of 4, if there's any way to write this with a common base of that 4, for example, 64 can be written as 4 to the 3rd power, because 4 times 4 times 4 is 64, that when I do that, if that's the case, if I have these bases alike, then these exponents must be equal to one another. If both are 4 raised to some power, then the 3x must equal to 3 in order for that to be a true statement. So you divide both sides by 3, and you'll find out that x is equal to 1. So my solution for x to this problem is 1, and it checks quite easily, because 4 to the 3 times 1 power, or 3rd power, is equal to 64. Good enough. I've solved that equation. Here's a similar problem to the last. And because I have a base of 4, if there's this chance that I could write this as 4 to some power, then I will. And so I can now set their exponents equal to one another since their bases are alike. So on the left I have an exponent of 3x plus 5. On the right I have an exponent of 2. I subtract 5 from both sides. I have 3x equals a negative 3. I divide both sides by 3, and I get my solution of a negative 1. And again, I could put it back in here to check it. 3 times a negative 1 is a negative 3. Add 5 to that gives me 2. I have 4 to the 2nd power. That is equal to 16. I've checked it without even writing anything down. I just needed to know for my own sake that it worked. And that's what you could do as well. Unlike the previous two examples, it's not always possible to take one side of the equation and write it as the same base as the other raised to some power. 13 here on the right side of this equation can't be written as 4 to some whole number power, and nor can I even figure out what that would be. So what I'm going to do when I'm solving exponential equations, if I would like to take the logarithm of both sides of the equation, I have to do it to both sides in order to keep the balance, I may. So what I'm going to do is I'm going to write in front of each of these expressions the word log. But what I'm doing is I'm taking the log of both sides of this equation. And the reason I'm doing that is because that allows me to use one of the properties of exponents, or logarithms, which says that if I have this log of some number raised to a power, I can bring that down in front. And so I'm going to bring this x in front, and I'll have x times the log of 4 equals the log of 13. And now what I'm going to do to solve for x, I want to get this x alone, and it reads x times the log of 4. Then I'm going to divide both sides by the log of 4. And x will be found by taking my calculator and hitting the log key. It'll open parentheses, type in the 13, close the parentheses, hit the divided by key. It won't look quite like this on your screen. Hit the log key, it will open, put the 4 in, close it, and hit enter. And when you do, in this particular problem, you get 1.85, and I'm rounding that off, so it's approximately 1.85. So my check, if that's my answer, 1.85, is to take 4 and raise it to the 1.85 power. So would you do that? 4 caret 1.85, and see if it is approximately equal to 13. That's all I'm doing to check this, is to see if it's approximately equal to that 13. And it does check. If I solve an exponential equation that happens to have an e in the problem, it's often very advantageous for me to not take the log, L-O-G, of both sides, but to take the natural log, Ln, of both sides. Because taking the natural log of e might allow me to reduce something to 1 here. So what I'm going to do is I'm going to take the natural log of e to the minus t. Therefore, I have to take the natural log of 0.01. And as I have in the past, my unknown, I'm looking to solve for t as an exponent over here. I'm going to bring that down in front, and I will have a minus t times the natural log of e equals the natural log of 0.01. Well, I want to get t alone, and I would like you to notice, however, that what I have multiplied times it is the natural log of e where the base is e. And we have said that the log of anything where the base is the same is equal to 1. That right there is equal to 1. So I have a negative t times 1 here. Or basically I have a negative t equals the natural log of 0.01. And I don't want a negative t, I want a positive t, so I'm going to divide both sides by a negative 1. And if you would take the natural log of 0.01, just hit enter, that's going to give you a negative 4.61. When you divide that by a negative 1, you'll get a positive 4.61. And there's my solution for t. All I would do to check this is I would take my original equation, e to the negative, t is equal to 4.61, so I need you to go e caret negative 4.61 and tell me if it's approximately equal to 0.01. And I'm sure it is. When you solve logarithmic equations, for the most part, what you're going to need to do is if there's multiple terms on a side, you're going to need to simplify it and write it as a single logarithm, and then you're going to write them in exponential form. So you've got to remember back to your skills of taking a logarithmic equation and writing it in exponential form. Please remember that a logarithm is an exponent, so this represents an exponent. There's my base. So in exponential form, I would write this as 9 to the 1/2 power equals x. Well, I'm asking you to take the square root of 9, and that's going to be equal to a positive 3. You're not going to give me a negative 3 as an answer, and that's because there's no way to take a positive base and raise it to a power and get a negative result. You can't take a positive base and raise it to a power and get a negative result. So you're not going to give me plus or minus 3, you're just going to give me a positive 3 here. And you could check this by the change of base formula. That's the best way I can think of. The log of 3, where the base is 9, so my check would be by taking the log of 3, I want you to practice the change of base formula, and dividing it by the log of 9. The change of base formula says take the log of this divided by the log of that, and you should get 0.5 with your calculator. Again, let's solve another logarithmic equation. So I have the logarithm that is a single term, so I'm ready to go right into exponential form. So I'll take my base, raise it to this power. So 2 to the 6th power is equal to the 8 minus 2x, and I'm ready to go ahead and solve a linear equation. 2 to the 6th power is equal to 64, and I'll subtract 8 from both sides, and I'll get 56 equals a negative 2x, and then I'll divide both sides by a negative 2, and I'll find out that x is equal to a negative 28. Again, right here, x is equal to a negative 28. The only way I can think to check that is to plug a negative 28 in there for x, so a minus 2 times a minus 28 is a positive 56. So what you're taking is the log of 8 plus 56, where the base is 2, or in other words, you're taking the log of 64, where the base is 2, and again, I'm doing my check right now. Change of base formula would tell me to take the log of 64 and divide it by the log of 2. I'm using the LOG keys because it's the easiest for me. I could use LN keys if I wanted. And I just want to know if that is equal to 6. Again, log, open parentheses, 64, close them, divided by, hit the log key, open parentheses, 2, close them, hit enter, and you should get 6 to check that. Here's my answer. This is my check. Please remember that when you solve logarithmic equations, we've been solving exponential equations where for the most part you take the log of both sides. But when you solve logarithmic equations, if you can simplify terms, and you must actually before you can write it in exponential form, you should do that. So here I have the difference of the log of two things. Well, I'm thinking quotient then. That's one of the properties. So I need to write this as the log of x plus 9 divided by x. And because there's no base written here, I'm to understand that that's a base of 10. And that should equal 1. So I've used a property of logarithms. It's a quotient rule. And now I'm ready, because this is a single logarithm. I'm ready to write this in exponential form, so I'll take my base raised to this power. So 10 to the first power, which is 10, will equal x plus 9 over x. Now, I'm ready to solve this equation, and so in order to solve it for x, I'm going to multiply both sides by x to get the x out of the denominator. So 10 to the first again is 10, so I have 10x on the left is equal to x plus 9. So I'll subtract x from both sides, and I'll have 9x equals 9. I'll divide both sides by 9, and I'll get a solution of x is equal to 1. Now I would check that by putting a 1 in here and a 1 here. So again, my check would mean 1 plus 9 is 10. So I'd be asking you to take the log of 10, where the base is 10. Well, we know that's 1. And then I'd be putting in a 1 there, and I want to subtract the log of 1, where the base is a 10. So again, I can do this one without a calculator. The log of 10, where the base is 10, is equal to 1. The log of 1 is always 0. I don't care what the base is. And 1 minus 0 is equal to 1, and that's what I wanted it to be equal to. Again, my answer is 1, and that was my check. This concludes the section that involves solving exponential equations and solving logarithmic equations. It's actually quite fun, I think, because you get to use the properties, and you get to solve for an unknown that is usually kind of unreachable.